Hi everyone, I'm Raphael. I'm a grad student at the University of Virginia, and today I'm going to talk to you all about my work over the last year on multi-wavelength views of an exploded strip star as part of my VSGC fellowship that I've been kindly supported by for the last year. Okay, so first of all, to back up from that title, what do I mean when I say an explosion of a star? So when I'm talking about an explosion of a star, I'm talking about what we call a supernova. So in my case, what I'm talking about is the explosion of a star that's more than 8 times the mass of our sun. And this explosion happens once the star starts fusing iron in its core, right? So basically, once this iron fusion starts happening, the star will lose the battle against gravity, collapse, and then explode. So this will happen in all stars more than 8 times bigger than our sun, although it will not happen in stars like our sun, actually. So our sun will not go this way, but stars that are more than 8 times bigger than that will. So supernovae are super cool and explosive, but they're also really important. And the reason they're important is because supernovae are actually how we get a lot of the elements that are really vital to life on Earth, like calcium, iron, sodium, magnesium. All these elements that we have here on Earth have come from exploding massive stars, billions and more millions of light years away that have propagated to us throughout the history of the universe. Okay, so you might have just noticed that I said most of these explosions happen millions or billions of light years away, right? So stars explode about once every 100 years on average in a galaxy, so we're actually overdue for an explosion in our own Milky Way. But because of this, most of the supernovae that we've seen, so we now discover thousands of these a year, happen very far away from us. And because of that, they're what we call transient events. They happen on scales of weeks to months, right? So we can only see them for 50 to 100 to maybe 200 days at a time. And very importantly, we cannot see the stars before they explode because they're not bright enough in these galaxies far, far away. So because of this, we actually don't understand that well how these stars work, especially in the period right before they explode. We understand in general that stars are like onions. They have different layers made up of different elements, and these explode in either core collapse supernova or stripped envelope supernova, where the star has already lost some of its outer layers before it exploded. But we don't understand the specifics of the last 100 to 1,000 years before the explosion, which may be really important in informing yields and how much of each type of element gets down to us here on Earth eventually after these stars explode. So we really want to understand how exactly these explosions work, and specifically actually how the stars work before they explode themselves. Okay, so one way that we can actually do this is that some stars lose a lot of mass before they explode. We know this because stars in our own Milky Way, like Eta Carina, lose lots of mass. Now, Eta Carina and of course every other star in our Milky Way that's done this has not exploded yet. But as I'll talk about in a minute, we've seen clear evidence that a lot of explosions in our other galaxies happen after the star lost a lot of mass before it exploded. So then when it explodes, the exploded material starts to catch up to the material that was lost. And this actually sustains the supernova for a much longer time. So, as I just said, right, as after the star explodes, the material will move outward very quickly and catch up to the much slower material that was lost before the explosion. Okay, so basically, yeah, interaction allows us to see the history of the star that exploded in ways that a typical supernova does not. This interaction between the exploding material and the material lost acts as a time machine, allowing us to understand these critical 100 to 1,000 years before the explosion from the explosion itself. That's a lot of explosions. Um, right, so while a typical supernova evolves on timescales of 100 days, the sustained light that we get from this faster material slamming into the slower material allows us to understand the whole burst system of this explosion and see the explosion for longer in general. Okay, so some stars explode after losing all of their hydrogen and a lot of their helium, right? So these stars are very strange because they must have been highly stripped, so they must have lost a ton of mass, and then they explode right after they lost all of that mass. So the star will actually explode into the helium-rich material that was lost in the last couple of years before its explosion. So how do we figure out more about how these explosions work, these very rare and unique explosions? Right. So actually, one thing that I sort of alluded to before, but right, these supernovae are not only sustained for a longer period of time, but actually they emit at more wavelengths than normal supernova do. So we usually see a supernova at, if we look at the electromagnetic spectrum, at optical, infrared, and ultraviolet wavelengths. But actually, because you have fast material slamming into slow material, in these interacting supernova, we get shocks. And when you get shocks, you can actually get X-ray and radio emission, extending the window over which you can see the supernova and allowing us to better model what was going on in this complicated explosion environment. Okay, so how do we get X-ray emission, though, more specifically, right? So these shocks will heat things up to 1 billion degrees and generate X-ray emission directly, right? So most things on Earth have very much lower temperatures than that, so they emit at optical or infrared wavelengths. But these shocks are so hot that they just emit right at X-ray wavelengths, and we can use fantastic NASA telescopes like Chandra in outer space to detect this X-ray light because, of course, X-rays cannot penetrate our atmosphere. X-rays are absorbed by our atmosphere, in fact. So that's how these X-ray lights are, X-ray light is detected. But how do we get radio light from these supernovae? So to get a little bit into the physics, when you have these shocks, you'll have a strong magnetic field. And in that strong magnetic field, if you have electrons that cycle, you'll actually get radio waves directly from that cycling motion of the electron. So we get radio waves at these long wavelengths, right? So radio waves are the biggest waves when you think of light as waves. And actually, because of this, we have to use very special techniques where we combine dishes from around the world to create one nice high-resolution map of a radio explosion, right? So we can use a technique we call interferometry. Because radio light comes in at such long wavelengths, we can use big dishes spread across half the world to detect things in high resolution at radio wavelengths as well. Okay, so this whole time I've been talking in general, but my project for the VSGC this last year has involved looking at one helium-rich explosion in particular, which lost a lot of helium right before it exploded, like I talked about before. So for this object, we modeled the radio and X-ray emission, and we found that it was losing mass before it exploded at a rate 1,000 times higher than anything seen in our Milky Way, and actually really 10,000 times higher. There's only been a couple of weird things in our Milky Way that had high mass loss that was in any way comparable to this pre-explosion mass loss that we measured from our radio and X-ray observations of this supernova 2023 FYQ. So we also find that the mass is being lost at high speeds. And in fact, actually, this was the first time we found a helium object that was losing lots of helium before it exploded detected in the radio. So these are actually intrinsically rarer explosions because they have to be stripped of more of their material. And because of this, we haven't found the one in the radio before. So this one was the first time on the paper that I led that was detected at radio wavelengths, and then we were able to infer the mass loss history from. So how does this happen, though? How does a star lose mass at such a high rate, 1 trillion times higher than our sun, and at such a high speed? So we think this comes from the fact that the star is in a binary progenitor system, is what we say, right? So these stars are probably in a system where they have another star orbiting them that they lose a bunch of mass to, then they explode and run into the material that they lost. So this makes sense because we've actually found that over 60% of massive stars may be in these binary systems. And as the large star expands over its lifetime, the mass transfer can ramp up and reach these elevated levels that we don't see in our own Milky Way. So this would help explain how the rate is so high, although more work has to be done on modeling exactly how you get up to these rates of mass transfer, which we're working on right now here at UVA. So basically, yeah, the picture is you have these stars orbiting each other. There's lots of mass loss, then the explosion happens, runs into that mass loss, and we get nice emission across the electromagnetic spectrum. Okay, so in general, right, what I did over the last year is use this model for interacting supernovae as a time machine to understand the last 10 years before a star which lost a bunch of its helium exploded. Evidence so far suggests that not only this explosion, but lots of other explosions are in binary systems. But we need more investigation, which is ongoing here at UVA, to really understand the nuance and details of this binary interaction. So thank you very much for listening, and let me know if you have any questions. And feel free to check out the paper here. Thanks.